Is it
Okay,
fine?
that's fine. Thanks. Yeah.
How to stop sharing?
So I think we are in time. I should first of all remind you that the meeting will be recorded. By joining the MG16 meeting, participants automatically give the organizer consent to do so. So let's start. Well, maybe we can wait another minute for other person, and then we can start.
Hey, Christian.
Yes.
Are you going to start with Moradi, or because I just read the email about Stefano?
I think we can start directly with Dr. Boccioli and then with Dr. Moradi. We can shift the program.
You can just shift, because if you like, since I am co-author of that work, if you like, I can make a summary of the Stefano presentation. If you like.
Are you a co-author of the talk?
Mm-hmm.
We can ask Professor Filippi too what she thinks about.
I agree.
I agree.
Okay.
I mean, just to avoid you run into troubles with the program. I mean, I can do it.
So let's start with the session binary driven hypernovae of type 1, 2, and 3. And the chairpersons are myself, Cristian Cherubini, Dr. Carlo Luciano Bianco, and Professor Simonetta Filippi. And the schedule starts with the first talk by Dr. Campion, Stefano Campion, who told us that he will not able to give this talk today. So Dr. Ueda is kindly giving the talk, as far as understood. Okay. So thank you, and let's start with Dr. Ueda. The talk is neutrino and gamma ray production from proton-proton interactions in binary-driven hypernovae.
So thank you. Let me share my screen now.
Well, 30 minutes. Sorry, we are gonna stop 5 minutes before to questions. To have questions.
Yes, thank you. I will summarize. Probably will be shorter than that. Let me go. Oh, here we are. Right. I suppose you are seeing my screen now. So good morning to everyone. Thanks for the organizers. I am going to give this talk on behalf of Stefano Campion. He's sick. I just knew that a few minutes ago, so I will make a brief presentation of his results. So as you see from the title, is on a neutrino gamma ray production from proton-proton interactions in binary-driven hypernovae, which we make in collaboration with David Melon-Fuchsman and myself. So first of all, of course, we would like to know what is a binary-driven hypernova. This is the main, and how these proton-proton interactions can occur in this environment. So binary-driven hypernovas are progenitor of gamma ray bars in a model of gamma ray bars, especially for the case of long gamma ray bars we are here speaking about. So in this model, you have start with a binary, as the name says, in which you have a carbon-oxygen star, and this carbon-oxygen star has a neutron star companion. Then this carbon-oxygen star makes a supernova explosion from a core collapse. And so this supernova explosion, part of the matter which is expelling the explosion, is accreted by the neutron star companion, which is in tight orbit. And this is allowed by an enormous emission of neutrino from the neutron star companion. And this allows the neutron star to increase its mass, reach critical mass, and collapse into a black hole. At the center of this, of the carbon oxygen, the exploding carbon oxygen star, you have the formation of a neutron star, of course. So these systems at the end, they will produce a neutron star black hole binary if the binary keeps bound. But this is not the topic, a specific topic of this work. So we will have this matter, and you have the black hole, and you have all these baryons expanding around, and you have the process of black hole formation. In this process, as you know, probably from the models of gamma ray bursts, but it is thought that the emission, the prompt gamma ray emission, is produced by emission of electron-positron pairs. There are different mechanisms for which these electron-positron pairs can form, and one of these is that you have the magnetic band possibility. This is not a talk about electron-positron pair formation, but just to give you a flavor about that. So you have the black hole, which it was formed and from the collapse of the neutron star. Then you have the magnetic field lines, which are still there, which just were trapped there in the collapse of the neutron star. The black hole is rotating, and at the beginning, this magnetic field can be huge, and it can induce an electric field by gravitomagnetic effect between the rotation of the spin of the black hole and the magnetic field. There is a huge electric field is induced, and this electric field, if the magnetic field is overcritical, then the electric field can be also overcritical and create electron-positron pairs. This is one possibility, but this is not the only possibility to form that electron-positron pair. The issue here is that these electron-positron pairs start immediately to expand. And as they expand, they should expand into this system. So what you have in this is the picture I was describing. You have the accretion process, you have the core collapse, expanding matter. Here you will form these electron-positron pairs around the black hole, and they have to start in this environment that you are seeing here. So what is important for this presentation and for this work is that you have different regions in which they have different densities. So in this region, here is the neutron star collapsing, okay? And here is the neutron star formed from the supernova, okay? Here, this region is of high density, while this region is of very low density. So what do we mean by that? So you see here a profile of density, for example, and you have in different directions. You see here as you go from here, you see mass profiles, for example, as a function of the distance along different directions measured from this point. So you see this region of low mass and these regions of high mass. So the dynamics of this electron-positron pair is completely different because it's loaded by different amounts of baryons. And so what we will have is an electron-positron pair expanding loaded with baryons, and these expand and can be, depending on the amount of baryons it is carrying, it will reach some ultra-relativistic velocity. So the gamma factor, the Lorentz factor that it may reach depends on this amount of mass. So in some regions, I can anticipate that. So in this region, the Lorentz factor can be very large, while of the order of 100 or 1,000, while when expanding the electron-positron pair along these directions is of the order of 3, 4, 5. So it's completely different dynamics. And especially what we are interested in this work is that you have this electron-positron pair forming, expanding, carrying baryons in its front, and these baryons are going to interact with the baryons which are still not absorbed by the electron-positron pairs. And so you will have this sort of a proton-proton collisions from these protons that are carried by the electron-positron pair, and they acquire some large gamma factor with respect to the ones which are here in this remnant. So we are interested in computing. This work was mainly dedicated to the emission of neutrinos. We were interested at the beginning in the emission of neutrinos from this proton-proton collision. But we compute also, of course, all the other products of this emission, and also especially the photon emission from this. So we show here what is the photon emission and the neutrino emission from these proton-proton collisions along different directions in this process of electron-positron pair expansion, carrying baryons interacting with the baryons, which are essentially at rest with respect to them. So this is a profile of the gamma factor of this electron-positron pair with baryons, carrying baryons, and this is the density of the electron-positron pair and the density of the remnant. So let's move ahead. So what these proton-proton interactions are producing? So these are typical calculations of proton-proton interaction decay chain. So we will obtain these pions, then they decay into muons, neutrinos. So there will be primary neutrinos and there will be secondary neutrinos. And then we are interested in obtaining, so this neutrino here, this protocol neutrino here, and this gamma, these photons here. So these are our main interest. We will want to know if by any chance high energy neutrinos could be not only emitted, but eventually detectable from this system. The answer is yes, there are. By high energy, I mean here we will see is only GeV neutrinos that we are going to produce in this system, not more than that, because of the Lorentz factor of these protons are of the order of 5. So you cannot go farther than 5 GeV or so for these neutrinos. But the issue here is that even as we will show that the luminosity, the flux of neutrinos is huge, is very big, but from the cosmological distances of GRP, there is no hope to detect this kind of neutrinos. So we'll show this by numerical simulation. So here, what are the ingredients of our simulation? So we have, of course, the supernova remnant, which is obtained from numerical simulation. So essentially, we need the density profile obtained from this simulation, which were three-dimensional simulations of the smooth particle hydrodynamic, three-dimensional simulations presented in a paper we published 2 years ago, 2019, in Astrophysical Journal, with Laura Becerra and Chris Fryer. And so we have that density profile at the moment of explosion. And so we have that. So we have the mass of the ejecta, we have the profile of the initial profile of these baryons, which is roughly goes as r to the minus 2.8. Then we have that. And we have also the initial velocity profile of the remnant, which is essentially with respect to electron-positron pairs, which are ultra-relativistic, we can consider essentially at rest. And then the plasma, the total isotropic energy of the electron-positron pair, this is a number which we can change. We can explore different values, but we will take something like a few 10 to the 53 erg as an example. One key parameter here is what is called baryon load. So the ratio between the baryon rest mass energy to the electron-positron pair energy. So this will discriminate the two regions. As I was mentioning at the beginning, there is the region of low density. It means low baryon load, while you have the region of high density is region of high baryon load. So And here we have baryon loads of the order of 10 to the minus 3. And here we have for the order of 50, 100. So it's a completely different situations. Since in this, when the baryon load is low, the asymptotic gamma factor of the electron positron per plasma is of the order of 1/V, and so will the ratio of the order, we can reach values of the order of 10 to the 3. But here there are two ingredients. It's not only the question of the load of the Lorentz factor, but it's also a question of density. So when we speak about fluxes, so from one side, here we have large, higher energies for the proton, but very low energies, but very low density of the target protons, so the proton-proton collisions. Well, here we have lower energy. Here we have lower energy for the protons, but high density of the target. At the end, it comes out that this is the region which is important from the point of view of flux, and in which the flux of the emission of photons and neutrinos is big, while here is very low. Let's go to here we present some numbers of typical numbers of the conditions we have in this for this collision of proton-proton. Because I was just mentioning, here gamma is at most 6, and here gamma is at most 10 to the 3. And density of particles here is 1 particle per cubic centimeter, while here is of the order of 10 to the 23, 10 to the 25. Due to the results of the high density region, so this is the gamma factor of the interacting protons, and here is the density of this front shell of electron-positron current protons. So here is the maximum Lorentz factor, density, and total, so the maximum energy of the protons of the order of 6 GeV. But we are interested in the particle spectra, so in the luminosity actually. So this is what we are obtaining here. So this is the spectrum. This is the spectrum of the photons from these photons going from the decay of pi 0. And in here, this is what you obtain. You see that the numbers, the biggest, the largest luminosity. So these radii are different. I don't know if I put here these reference points along the trajectory, this expansion of the proton of the shell. So this is R1, these are R2, R3, R4 are these positions. So this is the higher emissivity is obtained at this radius R1. Of course, this we have to integrate this in the volume to get actually the luminosity. You see, this is emissivity. These are power per unit volume. So we multiply by volume. If we take into account that these radiuses are of the order of 10 to the 10 centimeters, as you can see here. So you have something like this is actually, let me see. This is probably not the right plot. Yes, no, that's fine. You have to integrate. We'll give the numbers of the actual integration of these also in time, because you have to take into account also the decreasing speed, and then at the end we end with the numbers of the luminosity emitted. I will show that in just a minute. Here is the same for the neutrino. So you have here again the emissivities of the neutrino, and you start to see already here that they are pretty large, even compared with just one order of magnitude lower than the photon emissivity. Let's go probably to the let me see. We have this is the secondary neutrinos. Secondary neutrinos, we have the same order of magnitude. You see the energy of the neutrino here is of the order of GeV. And then these are again neutrinos, and then we go to the calculation of luminosity. These are the numbers we are interested at. Actually, here is a luminosity of the neutrino. So you see pretty large, the order of 10 to the 51 error per second, a few 10 to 51 error per second. That's in principle is a huge luminosity for a neutrino, but it's of last duration. You see, it lasts only for 1 second. It's a very short time. Why? This is because this proton, this shell decelerates. As it decelerates fast from gamma 6, it decelerates, and then you will not anymore be over the threshold for the proton-proton interaction. And so you can all these think is over. So it's only for 1 second you have this, so you have a sort of bars, 1 second bars of neutrinos of the order of 10 to the 51 error per second. So actually we have of the order of 10 to the 51 error in energy. That this is what is written somewhere here. So you see this is the total energy emitted in this process for the gamma, for the primary, and for the secondary neutrino, and then the muon neutrinos and electron neutrinos. So essentially we have photons of the order of 10 to the 52 erg, and a neutrino of the order of 10 to the 51. This is what we obtain from the high energy, high density region. But for the low density region, let me jump right. We go directly to the results. You see here again, here you see the numbers are completely different because of the density of the target photons. The target protons are those of the of the interstellar medium, are not the photons of the remnant. And so the density is spread low, and so the luminosity is low. Yes, of the order of 10 to the 42, 10 to the 43 error per second. So most interesting region is, of course, the one of the high density. And then we discuss the detectability of these, of the neutrinos. Of course, we compute the horizon, the neutrino horizon for this kind of system. So I mean that the distance at which you have to put the source to have a detection of one neutrino. We do that for superconductor, hyperconductor, ice-cube deep core. You see the distance here for the primary and the secondary neutrinos. In principle, you see the order of megaparsec. You could say, well, that's fine. No, that's not fine, because we are not speaking here about just the ordinary supernova. We are speaking about the gamma ray bars. And gamma ray bars typically distances are much larger than these densities. That this distance. So we are still very, I mean, almost local universe, by usually for these kind of systems, we have redshift of the order of 1, 2, and 3, and up to redshift 9. So we are speaking about gigaparsec distance and not megaparsec. And since the detection, you see the detectability, of course, goes as 1 over distance square distance. It dramatically reduces the probability of detection. So even if
minutes.
Yes, thank you. So even if the flux the luminosity is high, the rest frame of the source, then at the end the flux of the Earth is extremely low. So there is no hope to detect these GB neutrinos from this kind of sources. And the luminosity in photons, about the luminosity of photons, is also the order of 10 to the 52, but this occurs in 1 second and occurs in a region of high density. So we don't think these photons can be directly observed as GeV photons. because they are still in a very high density. So probably they will go into gamma-gamma interaction and produce additional electron-positron pair. So this is actually something that we would like to study in the future. How these proton-proton collisions produce this gamma, and this gamma again go into electron-positron pairs that go and again go how these new electron-positron pairs will enter into the dynamics of the previous electron-positron pair. So this is a question for the future. And the other question for the future is that we have in this binary-driven hypernovae, we have shown that some along the rotation axis, near the rotation axis of the black hole, you can expel particles, to expel protons at very large, at ultra high energies. They can reach energies even of the order of 10 to the 20, 10 to the 21 electron volts. So we plan to study the proton-proton collisions for those protons. So these can be very interesting systems, and we are looking forward for the new results, and that it can be actually very more promising in terms of the neutrino counterparts from those collisions. So this is the last. Yes, this is the last slide. So I stop here. Thank you.
Thank you. Let's thank the speaker. There's time for questions. Is there any question? I remind you that you can use the chat or the hand.
So sorry, I was a bit slow. I was trying to enter into the logic of Stefano presentation.
Okay, so if there are no questions, we can wait another minute and then start with the other talk. Could you please unshare the screen?
Sure.
Thank you.
Okay, good. Thank you.
Dr. Bianco has arrived. Dr. Bianco, can you hear us?
Sure. I can hear you very well.
Would you please check the chat too while I'm coordinating the talks? So the next speaker is going to be Dr. Luca Boccioli. Okay, we tried your presentation already at the beginning. I think that we can wait. Well, you can start by sharing your screen, and then we can start in time in 1 minute. So your talk is going to be general relativistic turbulence in spherically symmetric core collapse supernovae simulations. Okay, let's wait 1 minute and then we can start at 10.
Okay.
I remind you that we have 25 minutes for the talk, 5 for the questions, but I'm gonna tell you 5 minutes in advance when the final time is arrived. Okay. So I think that you can start. Thank you.
Okay. So hello everybody. I am Luca Boccioli, and I am a graduate student at the University of Notre Dame. And the work I'm going to present today has been done in collaboration with my advisor, Professor Grant Matthews, and with Dr. Evan O'Connor from Stockholm University. And you can also find it in this paper here that we published a couple months ago. And I'm going to talk about the role of general relativity in the context of turbulence in core collapse supernova. So first of all, how does a supernova work? Well, we know that stars more massive than 8 to 10 solar masses, they go through their life cycle. They burn hydrogen, they burn helium, then all the way up to silicon, until they look something like this. They have an iron core, and then in an onion-like shape, in an onion-like structure, they have all the lighter elements in the outer layers. We of course know that this is a simplistic picture, but it's good enough for what I want to talk about today. And supernovae mostly deal with the iron core. Now, the idea is that iron has the lowest binding energy of all the nuclei. So if you try to fuse two iron nuclei, there's no lower binding energy state you can reach. So you always lose energy. And we know that stars need the energy of nuclear fusion to counterbalance the gravitational pull. So once they have a core made of iron, the only thing they can do is collapse, and they start collapsing. And this collapse will very quickly make the center of this iron core reach nuclear saturation densities, above which the nuclear force becomes repulsive. So you can think of the center of this core becoming basically an impenetrable sphere. And at the same time, you have all these outer layers collapsing on top of it. And what happens is that basically they bounce off this hard sphere that we call protoneutron star, and eventually is what will become the actual neutron star. And so this bounce will generate a shock wave that will start propagating outwards. And this is what 50 or 60 years ago people thought the supernova was. You form this shock will reach the outer layers, and this is what we see in the sky when we observe a supernova. And this is almost correct, because unfortunately we know that now this mechanism doesn't quite work, because the shock, as the outer layers keep collapsing, the shock propagates, but eventually it stalls at some fixed radius r. And so it stops here, and it stays there for a few hundred milliseconds, fighting against the material accreting down. And so at this point, if you want to trigger an explosion, you have to push the shock all the way to the outer layers. And to do that, you need to inject some extra energy in the layers behind the shock, and effectively push the shock and let it propagate outwards. And this extra energy is now pretty well established, mostly comes from neutrinos. So the protoneutron star, you have a very high flux of neutrinos that are coming out because you have, you're forming a neutron star. So you're turning matter into neutrons. And this generates a lot of neutrinos, and there are other mechanisms that can generate neutrinos as well. But the bottom line is that there's a very high flux of neutrinos. Now, some of these neutrinos statistically will interact with the matter right here behind the shock. And so this will effectively push the shock outwards, and it will help it fight the accreting material. And however, this energy is not enough by itself. You need some extra mechanisms that are able to transfer some energy from the neutrinos to this matter here. And arguably the most important one is the neutrino-driven turbulence, and that's what I'm going to talk about today. So this is turbulent material that's present behind the shock, and I'm going to talk about how neutrino-driven turbulence work in just a second. Okay, so we established that we need this extra energy to effectively trigger the explosion. And in some cases, this extra energy will actually be enough to trigger the explosion, but in some other cases, it will not be enough. And what happens is then that the accreting material wins, and everything will fall back onto the protoneutron star, and you form a black hole. And all of this happens on the time scales of about a second. Okay, so what is neutrino-driven turbulence, or more precisely, neutrino-driven turbulent convection? And during this talk, maybe sometimes I will talk about turbulence and convection interchangeably. It's not exactly the same thing, but one causes the other. So maybe I will say turbulence or convection interchangeably. Okay, so what you're looking at here is a 3D simulation of a supernova from Radice et al. And what you're looking at is a slice of the star taken at 200 milliseconds post bounce. The shock has reached 300 kilometers. And as you can see here, there's a lot of turbulence going on behind the shock. And as I said, you have a lot of neutrinos that are coming out the protoneutron star. Now, these neutrinos will interact with this material and therefore will increase its entropy. So in a very simple one-dimensional model, if we assume that all of this is spherically symmetric, we can justify this by saying that as a function of radius, the entropy is quite low in the center. And then because of these neutrinos interacting with the matter, the entropy increases because basically these neutrinos are transferring energy to the matter. However, beyond the shock, as I said, there's just iron, and iron has a pretty low entropy. So there has to be a maximum of the entropy. And if you run spherically symmetric simulations, this is exactly what you see. And as you can see here, there's a negative entropy gradient. And we know that negative entropy gradients can trigger convection. So the idea is that you have this turbulence going on, and some of these turbulent eddies, some of these turbulent bubbles will rise through the entropy gradient, and then they will transfer their energy to the matter behind the shock. And so this transfer of energy is what I was talking about before, is what you need to effectively push the shock all the way to the envelope and trigger the explosion. And yes, that's exactly what I have. So now you might ask, okay, you're showing this 3D simulation. We see the turbulence. Everything you said is reproduced in this simulation. So why do we even bother with spherically symmetric simulations? Well, the problem with these 3D simulations is that they're very expensive. They take millions of core hours to run. They take months and months. Hopefully, with the exascale computing that's coming online, that will cut this time by a large amount. So we're going to have more efficient 3D simulations. But still, the parameter space of supernovae is very large. So to explore it, you would need to run a lot of these 3D simulations, which is not feasible. Spherically symmetric simulations, which they're also called 1D simulations because you're just evolving the radial component. They're very fast. They take a few hours to run, maybe. The problem is that clearly this structure is not spherically symmetric. So you don't have turbulence in these 1D simulations, and therefore you never see an explosion because you don't have that extra energy that I was talking about that pushes the shock. So all of the 1D simulations fail. A good compromise could then be finding a parametric model that enables us to mimic the effects of turbulence in 1D, and then these 1D simulations can then be run and we can explore the parameter space of supernova. And so what we did is look for such a model, and we found a very nice one from Couch et al. In 2020. Now, people have known how to model convection for a long time. They typically do it through something called mixing length theory. And Couch et al. Basically applied a refined version of mixing length theory to the environment of supernovae. And the idea is that you can take your favorite hydrodynamic code. They use Flash, and what these codes do is evolve, density, velocity, energy, and electron fraction. And then you add an extra variable, which is this turbulent energy, which is that extra energy that I was talking about. And they derived this equation in their paper by using Reynolds decomposition applied to the environment of supernovae. So it's for the thermodynamic. This is valid for the thermodynamic conditions of supernovae. And then you evolve this turbulent energy, and basically these two sources generate the turbulence through shear and buoyancy. And this term dissipates the turbulence. So you build up some energy in these turbulent motions, and then you dissipate it, and basically you transfer this energy to the matter. And okay, so what we, oh yes, just a little bit more on this model. The way it works is that you basically calculate this quantity, the Brun-Vasala frequency, in every region of your star. And this is just some acceleration, so it's always positive. And this part is the difference of two thermodynamic gradients. And whenever this quantity is less than 0, it means that that region, in that region, no convection develops. Whenever this quantity is greater than 0, convection develops. So once you know where convection develops, you have to tell your code or your model how strong the convection is, because as I said, in one dimension, for convection to develop, you need at least 2 dimensions, right? So in 1D, you have to tell your model how strong you want the convection to be. And of course, this depends on a parameter of order 1. And basically, this is called the mixing length, and it's the length that these bubbles will rise before being dissipated into the surrounding medium. So the longer they travel, the stronger the convection is. And then, the turbulent velocity can be thought of as omega times lambda. Of course, as I showed, it's a little bit more complicated than this, but this is the gist of the model. Okay, so what about general relativity, though? Because Flash, the way Couch et al. Used this model, which, by the way, it's called STIR, is they implemented it in a Newtonian code. But what happens when turbulence acts in a general relativistic environment? Well, to investigate this, we used a one-dimensional open source code, GR1D, which, as the name suggests, uses GR. And it actually can run with full GR, evolving a Schwarzschild-like metric, but it can also run with Newtonian dynamics, with something called general relativistic effective potential, which basically means that the dynamics is completely Newtonian, but inside the potential, the gravitational potential, you add some general relativity corrections, but the dynamics is Newtonian. So when you see GREP, just think of Newtonian dynamics. And okay, so to do this, first of all, we need the metric of GR1D. It's just some nomenclature, basically. It's not that important. The lapse function is defined through a potential phi, which eventually, in the non-relativistic limit, is the Newtonian potential. And the regular density becomes a conserved density, basically defined through the Lorentz factor, and then you can also work in which the velocity is defined like this with the GRR, the RR element of the metric. And okay, so since we want to put this model in a GR code, we need to write this equation in its GR version. And to do this, we treat this v squared term. We treat this as a scalar, so in the same way that we would treat, for example, the electron fraction. And so the left-hand side, it's pretty easy to derive. It looks something like this. For the right-hand side, we actually we say that, okay, turbulence happens as we saw before in the layers behind the shock. So that's quite far from the protoneutron star. And there, the general relativistic effects are pretty small. So we can treat this as a source term and just put this in the Einstein equations as it is. And therefore, it simply picks up a factor of alpha x in here. However, the omega and lambda will be different in general relativity. So lambda is actually pretty easy. Instead of g, you have this d phi dr, where phi is this oops, I'm sorry, or phi is this factor here coming from the Laplace function. And then, as I said, in the Newtonian limit, this actually becomes g, which is just the local gravitational acceleration. So lambda is pretty easy. Omega is a little more tricky. So you can actually derive a form for omega exactly for a hydrostatic fluid. So whenever this V is 0, it's been done by Kip Thorne in the 60s and redone by other people in a more modern formalism. And we did it for our metric, and it's not that hard. However, when your fluid is moving, as it is in supernovae, then you have you have to shift the frame of reference. So it's not that easy in GR. But as I said, since we already approximated our source term by saying that GR effects are pretty small in the outer layers, we do the same thing for the Brun-Vasala frequency, and we say, okay, we just replace VR with the GR version, or with the GR velocity, and it should be pretty close to the actual, fully covariant expression. Okay, so the main difference between these two is probably the inclusion of the internal energy inside in this gradient here, and which eventually will make the star more compact. Whereas the differences in this term are quite small, actually. So this is the main difference. Okay, so now we have our GR model for this turbulence. And what we did is, first of all, verify that if we run with the same setup of Couch et al., so with no GR, with just this GR, general relativistic effective potential. So basically, if we just use Newtonian dynamics, we obtain something that's pretty close to their results. What you're looking at here is the shock radius versus time. So these, for example, these simulations here, and we did it as a function of alpha. So for this simulation here, for example, you have an explosion because the shock stalls for some time and then eventually goes all the way to the outer layers. These simulations here, for example, are failed supernovae. So this will eventually lead to a black hole. And our results are slightly different. That our shock is pushed to a bit larger radii in this case, for example. But it's expected because we are using two different codes. And just for reference here, we show a 3D result for the same progenitor, same setup. And the dashed line is therefore the true result. So it's what we would like to mimic with our model. And you can see the same thing by looking at the convective speed. So this is the V-turb that I was talking about. As I said, we have a slightly larger convective speed, but overall, we obtain the same results. So now that we know that we are getting the same things that they do, we can switch the GR on and compare to the Newtonian one. And we see that, first of all, the range of alpha is different because you need a larger value of alpha in GR to obtain a similar shock dynamics. And the reason is, as I said, the star is more compact because you're including the internal energy in the definition of rho. And basically, this flattens the gradients a little bit, and therefore you need a larger value of alpha. You can see it in the convective speed as well. You need a larger value of alpha to achieve sort of the same kind of convection that you achieve in Newtonian. Okay, so now, as I said, once we have this model, we can explore the parameter space of supernovae. And the main thing that you can change is probably the mass of the progenitor star. And that's what we did. So actually, first of all, as I said, we want to reproduce this 3D result, right? So we need to choose our alpha in such a way that we are close to the 3D result. So we identified a range of alphas that give us something close to the 3D. And for those values of alpha, which are here for this is for the Newtonian one, and this is for the GR one. So for those values of alpha, we ran a bunch of simulations for different initial masses of the star. So this is the mass of the star. And when you see green, it means that that simulation, that star has exploded. When you see black, it means that eventually it will generate a black hole. And if you focus on sort of intermediate values, we know that here there are too many black holes. We know that we don't form as many black holes as from observations as we do in here. So we have to focus on intermediate values of alpha. And the first thing you notice is that in the Newtonian, this progenitor does not explode. In the GR version, it does explode. However, these higher mass progenitors here do explode in Newtonian, but do not explode in GR. And actually, they explode quite easily in Newtonian. So it's very easy to make these progenitors explode. So what this is telling us is that even though the effects on the turbulence itself, the general relativistic effects, are not that big, so that we can do all those approximations that I talked about, it's still the turbulence is acting on a star that it's whose structure is defined by GR. So it looks like general relativity can make a pretty big difference between when you look at the explosion as a function of mass. Now, as you can see, as you increase alpha more and more, these two will look more and more similar, and that's expected, because for a high enough value of alpha, everything will explode. Because, as I said, high values of alpha mean that you have a lot of convection, and so you're injecting a lot of energy in your system. So eventually, everything will explode. Nice. Thank you. So this is just it's not really that relevant, but it's something we are working on now. As I said, you can explore the parameter space of supernovae with this model, and you can look at the role of the equation of state, the nuclear equation of state, for example. And these are preliminary results, but it seems like the strength of explosion as a function of equation of state seems to be correlated with the central entropy and with the turbulent energy inside the proton-neutron star, and hopefully we can publish these results soon. But going back to what I showed before, we can compare our results to something that has been done already in the literature by Couch, who uses the same model as we do, and Suckbolt, who uses a different model. And as you can see, for low mass, Suckbolt obtains a lot of explosions, but we don't in neither of our models. Whereas for intermediate masses here, we do find explosions as Couch does for our Newtonian model, but we find a lot of, or not a lot of, but we find some black holes with our GR model, which seems to be the same as Suckbolt finds. So there's still some work to do. Our model seems to be in between these two. So there's still a lot of work to do. Eventually, we would like to see 3D simulations done with these many progenitors, which maybe it will come soon, maybe not. So the conclusion, the bottom line is that general relativity effects can change the explodability pattern, meaning the explosion as a function of mass of supernovae. So we would like to see more 3D and 2D simulations that use full GR, which currently are not many. People are still using this GREP effects, and in the future, we would like to use this model to explore the long-term behavior of supernovae and the effects of the nuclear equation of state, which I showed you a little bit about, and hopefully we're going to be able to submit it soon, at least on the archive. Okay, thank you very much.
Let's thank our speaker. Are there questions?
Yeah, yes. Very, very nice talk. Can you hear me?
Yes.
It's Remo Ruffini. And I noticed, first of all, that you are exploring a range of mass around 20 to 22 solar mass for the CO core. Or, if you look at all the GRB we are seeing explosion, usually the CO core is always standard. I mean, you can look some 25 supernova occurring in GRB, and the energy is standard, and the other characteristic is that mass is around 10 solar masses. Therefore, and of course, all this system explodes very beautifully and do not form a black hole. The black hole is formed later in the binary-driven hypernova for the accretion on the companion neutron star due to the supernova ejecta. Therefore, this is the first point I would like to focus. Well, of course, I'm very, very interested about your result, and I hope very much that you will visit us in Pescara and together with Grant Matthews and to discuss further. But let's go first for the universality of the core, CO core collapsing seems to be, at least in gamma ray burst, where we see the explosion of the order of 10 solar masses. The second point, of course, I will, independently of that, the consideration that you are doing for GR can be extremely relevant, not eventually for GRB, but by themselves to look for the formation of the black hole, direct formation for large enough masses. Apart from that, there is a curiosity, which, as you remember, we studied with Jim Wilson the problem of the explosion of GRB, and the characteristic of this explosion is that is driven by an electron-positron plasma. It will be very interesting to see if in this, and I know Jim has been looking, Jim and the co-workers, and especially Grant, has been looking to the possibility of having electron-positron pair for driving the explosion. Is any way that you could consider this possibility in your turbulent model? to see if you can open the gate to the electron-positron production, which we see drives GRB.
Yeah, so I mean, in these models, of course, there are a lot of electron-positron pairs that are being produced. Some of them are taken into account through the annihilation into neutrinos. So, when you calculate the opacities to neutrinos, we take into account the fact that some of these electron-positron pairs can annihilate two neutrinos, and so typically the more neutrinos you have, the more likely the explosion is. But that's the only way we are taking electron-positron pairs into account. We don't have. I mean, they are taken into account inside the equation of state through the photon production. But I know, for example, a lot of people have looked into electron-positron pairs that annihilate to sterile neutrinos, or beyond standard model particles, so that and that can also change the explosion. But so the only extent that we have electron-positron pairs here is through some annihilation, like standard annihilation to neutrinos. But there can be a lot more effects that can, for example, be with sterile neutrinos or things like this, which we haven't looked at, but it's definitely something that that can be interesting.
But in a certain sense, was the opposite case that we will be very interested, not that electron-positron pair go to neutrino, but if this turbulence in the neutrino can generate further electron-positron pair and drive the dynamic.
Yeah, I mean, that's that is not something we looked at, because as I said, this is a parametric model for turbulence. So we basically just say we have this amount of energy in the convection, and then we transfer this energy to the internal energy of the matter. But we don't see any. We're not taking this effect into account. So maybe there is room for improvement in that sense. We can investigate how turbulence can affect the electron-positron pair production, which it's something that this model is not taking into account.
And of course, there is also the possibility of magneto-hydrodynamic process, which have to be taken into account, certainly, because this object, in fact, one of the most interesting aspects is that very likely this the rotation of the core can be quite important and driven by the binary companion. And therefore, all this CO core could be fast rotating.
Yeah, I mean, being this a 1D model, we don't have a MHD or rotation, but that's definitely something that's why I'm saying the parameter space of supernova is so large, because there's rotation, there's MHD, there's a lot of things that can vary and can impact the explosion. Yes.
I look very much forward to your visit here or our visit there to continue this discussion.
Yeah, sounds good.
Okay. Let's thank the speaker again, and let's go on with the last talk by Dr. Moradi. And the talk is going to be GRB-SN association and the interferences of GRB 190114C for the Crab pulsar and the supernova remnant. Dr. Moradi, thank you.
Okay. Hello, everybody.
I kindly ask to anyone else to switch the camera off, and only Dr. Moradi must have the camera on.
Okay, let me share my screen. Okay, I think you can see well now. Okay, I have.
So I was telling it's you have 25 minutes. I'm gonna tell you 5 minutes before, and then we have 5 minutes left for the questions.
Yeah,
Okay, thank you.
I think I need less time because it's a very short talk and very straightforward result. Okay. Today I'm going to talk about this GRB 190114C and the role of its pulsar, which is remaining from its supernova explosion, which we call it a new neutron star in this model, which I will explain. First, I will talk about the radiation model and the way that we explain the GRB 190114C and the different component that their interplay plays an important role in the physics of radiation model and the observed the explanation of the observed emission in different energy bands. Then I will go to the story of this new neutron star, which has just born after the supernova explosion. And finally, I will seek a way to, I will try to find a way to explain how this neutron star can explain the energetic observed in the afterglow emission of this source, namely the GRB 190114C. Okay, the story that also Dr. Roeda explained a bit is that the radiation model is a supernova explosion in presence of the neutron star, which is around 10 to 11 centimeter far away, orbiting around each other. This radiation model has three main components. First is supernova explosion, and as a leftover, the supernova ejecta and the new neutron star from this procedure, and the companion neutron star. So this explosion will have the supernova ejecta accretion onto the companion neutron star and fallback accretion to the new neutron star. And different scenarios based on the different orbital period of this neutron star and the CO core will lead to the different observation in the different energy bands. Okay, the main idea of this radiation model comes back to the IGC scenario, induced gravitational collapse, that was mainly produced by the Ruffini, Rueda, Becerra, and later by Chris Fryer in Los Alamos. With their group, they developed the code. It was that to explain the association of GRB with the supernova, the supernova explosion with the GRB, because there were many observations of the GRB, which later around average 15 days, there were some optical supernova peak related to the same position of the GRBs. And the main motivation of this model was to explain this relation. And as you can see, there are here listed more than 20 GRBs, different energetics, and different redshifts, which have reported their peak of supernova. Okay, what happens in this system? We have supernova explosion, and the newborn neutron star, then accretion to neutrons, companion neutron star. If a system is compact and binary period is around 5-6 minutes, we'll have the black hole formation. And then we'll have fall back onto the new neutron star. Before going to the story of the new neutron star in this radiation model, I will talk a bit about the black hole and what is the fate of black hole in this system and what kind of radiation we expect and we observe in this system. As you can see here in the first moment of the black hole formation, when we have black hole formation, due to the strong magnetic field and the rotating black hole, we'll have some induced electric field which can produce pairs, and this is not only way to produce pair. One of the possible way is the Schwinger mechanism, which produce pairs, and these pairs, since the problem of compactness, they cannot radiate at that around the black hole. They start to expand, and at around 10 to 12 centimeter, there will be optical thin and will radiate the emission, which is in the MEV radiation, known as prompt, which we call it ultra-relativistic prompt emission phase. After having this procedure, magnetic field will be, because of this interaction of the pairs, magnetic field will be a bit down. We don't have this overcritical field anymore, and we have a perfect medium for magnetic field around the black hole and the injected electron and proton to this system, which will lead via synchrotron radiation to the observed jet emission. And here is the very interesting formula that relates the rotational energy of black hole to how this energy can be extracted by this rotational energy to be seen in the electromagnetic radiation. This is the case of GB9 As you can see, there are lots of observation in the different energy band. For instance, in the GEV, in this red part, in the prompt emission phase, the MEV radiation, this blue in the first part. And the most important one for this talk today is the X-ray afterglow, this black data points that which follow a power law, which has been seen in more than 300 AT BDHN, similar to 19/14C, which hints a universal behavior for the X-ray afterglow. The first explanation of this universality behavior that reveals in the X-ray afterglow was done by Ruffini et al. In 2018, which they considered the energy injection by this new neutron star together with the kinetic energy around the kinetic energy of the supernova ejecta will produce this radiation in X-ray and optical and radio also at around 10 to 12 centimeters away from the neutron star. So the main conclusion was that two main components are participating in this radiation. One, the kinetic energy of mildly relativistic expanding supernova, and the second one was the rotational energy of the fastly rotating this magnetized neutron star. Here we want to show that if the neutron star itself can explain energetically this behavior that has been revealed in the X-ray afterglow in the more than 300 GRB can explain this behavior or no. For this matter, first we assume that only rotational energy of the new neutron star to pay for this luminosity observed in the afterglow. It's very easy. We demand that the energy emitted in the X-ray to be equal to the rotational energy of the neutron star to pay by this rotational energy. And when we do so, a weird thing that appeared is that only we can explain after around 10 to 4, 10 to 3 seconds. And when we go back to the early moment, less than like 100 seconds, the answer, the configuration of the neutron star would not be physical, namely the unphysical configuration of neutron star is needed to explain the early observation of X-ray. For instance, sometimes one solar mass neutron star, which is a weird number, or initial period of 34 less than 1 millisecond, which shows that the neutron star would not be stable in this system. So what's the solution? Here we assume that for solving this solution, we assume that in addition to the new neutron star rotational energy, its gravitational binding energy also participate in the source of energy for the X-ray afterglow. And how we can introduce it, because in the when it is very highly rotating neutron star, in the beginning the shape is not spherical, and there would be some deformation from the spherical neutron star, which here we introduced by this eccentricity factor, which shows how it is different from the sphere. Using this eccentricity, we introduce the angular momentum, mass, radius, and the moment of inertia, which all are related to this eccentricity. So what's the story? One step to another one, not only the rotational energy of the neutron star is decreasing, but also the shape is changing. This changing of shape from one state to another one will release some energy, which will go to the which will pay for the X-ray afterglow, generally for the afterglow emission covering from radio to X-ray. This is the formalism. The T is the rotational energy, W is the gravitational binding energy. And here we use this formula. Why we use this? Because it has, as I showed you also for the black hole, this is like a golden formula for calculating how energy is related to the rotational angular momentum and velocity of the system when we consider the synchrotron radiation of the particle around that system. And this was first mentioned, if I'm not mistaken, by Wheeler, the importance of this. And the importance of this formula is that we don't need to consider which kind of radiation, multipolar or radiation or whatever is producing. Only we can explain by the energetic. And if we want to go to detail, we should find different kind of radiation that can produce such a formula. Okay, these are the how after solving this equation, we can get the evolution of energy and the evolution of the angular momentum of the system, of the ellipsoid, which can explain this energy. Okay, here I demand only in the case of GB9 the X-ray, since the X-ray luminosity and energetic is much larger than the radio and optical, and the luminosity and energetic is not comparable to the X-ray luminosity. So we equate the luminosity of the X-ray by the energy released by the Maclaurin spheroid, which the observed luminosity follow this relation, which AX is around 10 to 52, and alpha is 1.37 in the case of this GRB. And in the average, this can be applied for all the BDHN of type 1 that have this behavior of, or type 2 that there is no black hole present, and this alpha X average for more than 380 BDHN is around 1.4. So in principle, this formulation can be explained for all the GRB afterglow. Okay, these are the explanation. These are the results that we have got that can exactly explain this energetic by the Maclaurin spheroid. As you can see, this blue part is the contribution of the rotational energy. This red part is the contribution of the gravitational binding energy, and eccentricity, the maximum 0.83, and the initial period. Here the configuration, whatever we use, we can explain by a reasonable value for the new neutron star. For instance, 2 solar masses, radius around 10 kilometers, an initial value of the around 0.5 millisecond at 1 second, which shows that it's in agreement with this stability constraint, which should be less than 0.7. So in principle, this formalism can explain the energetics observed by the X-ray afterglow, and there is no problem in the stability of the new neutron star. But the main important thing is that we are looking at the shell. It's like that we can explain energetically what kind of radiation synchrotron, or the mechanism of the synchrotron, what it is. This should be in this context, we will not go to this problem. Okay, that's it.
Okay, thank you. Let's thank the speaker. Are there questions? No, no questions. Okay, so let's thank the speaker again. We have concluded the list of the talks. Could you please share the screen? Okay, thank you. We have concluded the list of the talks, but we can still use part of the final time for possible discussions. No discussions?
Yeah. Hi, Christian.
Yeah.
Here.
Yeah.
I don't know if Luca Boccioli is still around. Okay, here you are. I wanted to ask you a couple of questions about
Me
Of
too.
course.
Me too.
about your talk. The first one related to Remo Ruffini comment. In our simulations, what we are finding about that specific mass for the carbon oxygen star which explodes would correspond to your range of 25, 30 0H main sequence mass. So this is the range we are interested. And that was a comment just to clarify. And my real question is how this convective paradigm, I mean, this actually changes if you have a carbon oxygen star, because I think you are assuming all with helium and hydrogen layers. So what happens if the outermost layer are stripped off from the star?
So the convection I'm talking about is basically only happening inside the iron core. So the convection, this turbulence that I'm interested in, happens within the first second of the explosion. So it happens when the shock is at around 200 kilometers, and it happens right behind the shock radius. So it's still inside the iron core. Later on, so first of all, the simulations I ran, they only go out up to a second maybe post bounce, which means that in some cases the shock has reached maybe the silicon layer, but not more than that. And actually in my supernovae simulations, I only include the maybe I don't even I don't even include the carbon and oxygen layers, depending on the progenitor star.
Because the density profile inside that core is not very sensitive to the external layer. This is what you are saying.
Yeah. So basically whether the star explodes or not, it's mostly only about the iron core. Then the properties of the explosion, of course, they're determined by when the shock goes in the carbon and oxygen layer and in the envelope, that will determine the properties of the explosion. But whether the star explodes or not, it's mostly just the iron core, basically. Yeah.
Good. That answers my question.
Okay.
I have one question. This negative gradient of entropy, which causes some instability, do we expect any radiation, electromagnetic radiation from these instabilities, or can we?
I mean,
can you hear?
Yeah. So these convective motions not really emit any significant radiation, I would say. It's it's basically, it's for some, you can think of this as basically the convection that happens maybe inside the sun. Of course, the thermodynamic environment is a little bit different, but the idea is the same. So it's these bubbles simply bring, they transfer energy from the inner parts to the outer parts, but there's not a lot of like radiation emitted during the process. I don't know if that answers the question.
Yes, that's what. Thank you.
Yeah.
Ask you one thing. I have some curiosity regarding the turbulence model you're using. As far as I understood, you're using a Reynolds decomposition. So essentially, you are computing mean values, and you are assuming a spherical symmetric conformation distribution for this type of behavior. You are using a first or second order turbulence model. I mean, the closure.
So
I'm not expert in turbulence in relativistic context. I know better lambda omega and kappa epsilon models in k epsilon models in standard fluid dynamics. So, I mean, you're using something like that?
So, I mean, I'm not an expert on this. If for the closure you mean so what do you mean by closure? So it's the way you relate the turbulent velocity.
Fluctuations, yeah. The order of fluctuations you arrive. Usually you have a first order, which is the simplest model of turbulence, then the second order, which is the one anyone practically uses, or you have full hydrodynamics, no? First, and I would like also to understand what is the relation with full numerical simulations. How good is this approximation? I'm curious.
So you basically we are mostly simulating the convection resulting from the turbulence. So in the Reynolds decomposition, when you do the Reynolds decomposition, you basically average everything, and I guess we stop it at first order. So we don't include any like v squared terms, and so that's the first thing. And then when you compare to full numerical simulations in the gain layer, it's pretty good. I mean, of course there are some differences, but at some point I showed the profile of the convective speed, and with respect to 3D, it's the agreement is pretty good. If you try to go inside the protoneutron star where things get more complicated, then the model is not so good. We still see some convection in the protoneutron star, but it's much less than what 3D simulations see. So it's all basically, this model works for the gain region of the supernovae. So it's very like model specific or very environment specific. So it's yes, and again, it's the model is the same, basically the same one that people use for stellar evolution, like mixing link theory for the sun or like for stars. So it's very different from, like, I know when you go to like neutron star mergers and things like that, people use large eddies models, and those are completely different, and they're more accurate, but because also they work in more dimensions. We only work in spherical symmetry.
Okay, thank you.
Thanks.
Other questions? Dr. Bianco, are you connected? Now what should we do? Should we wait for the end of the Zoom recording, or?
What time is the official end?
Maybe you can discuss some.
Okay, so I think that we can conclude here because there are no other questions, and the Zoom recording should.
Okay.
Here it is. Okay, Carlo, Dr. Bianco, could you please tell us how to conclude the session?
Well, we just log out and the session will close itself.
Okay, so we have to go out and
If we have
automatically.
no other questions, just log out and the session will close.
No, there seems that we have concluded the discussion. So I would like to thank the speakers and the participants again, and we can conclude this session. Thank you.
Okay.
Thank you.
Bye.
Bye.
Nice day.
Bye-bye.
Bye.
Bye.
Carlo, cosa faccio? Faccio esci da riunione o termina riunione per tutti?
Ah, tu puoi farlo. Ok, allora fallo. Termina per tutti.
Termino.